Hi everybody, how are you today? I have sent you a revision paper about complex number. This revision paper contains about 6 exercises. I hope we can solve it in these 4 days. It is a good revision. Today we are going to solve the first exercise, the first problem. It is a very important problem. Please watch it, write the notes, and if you have questions, you can ask me next time. So, 1 second. In the complex plane OUV, consider the points. We have the points. We have the points A of fx minus 2i, yani ZA equals minus 2i, and ZB equals 1, Zm equals Z, and Zm prime equals Z prime. This is the given. So we have given, it is given that ZA equal minus 2i, ZB equal 1, Zm equal Z, and we have this relation between Z prime and Z. Z prime equal 2i Z bar over 1 minus Z bar, with Z different from 1, since the denominator is different from 0. 1 minus Z bar different from 0, in Z bar different from 1, so Z different from 1. Part 1. Write Z in the algebraic form in case Z prime equal 1 plus I. Write Z in the algebraic form if Z prime equal 1 plus I. So we put instead of Z prime 1 plus I. So I put 1 plus I equals 2I Z bar over 1 minus Z bar. And I solve for Z bar. So write Z in the algebraic form in case Z prime equal 1 plus I. So I replace Z prime by 1 plus I. So I have replaced Z prime by 1 plus I. Cross multiply. We get 2I Z bar. 2I Z bar times 1 is 2I Z bar. 1 times 1 is 1. 1 times I is I. Minus I Z bar minus Z bar. So cross multiplication. Then I bring the unknown Z bar to one side. 2I Z bar minus I Z bar. Let's see, it becomes minus I Z bar. I bring it to the left side. Let's see the 3I Z bar. Minus Z bar plus Z bar equal 1 plus I. First, I take Z bar common. It will be Z bar into 3I plus 1 equal 1 plus I. So Z bar equal 1 plus I over 1 plus 3I. So it is easy here to calculate by using the calculator. by using mode 2, which is mode complex. I put fraction 1 plus I over 1 plus 3I. Then the calculator will give Z bar equal 2 over 5 minus 1 over 5I. This is the Z bar. Z is the conjugate of Z bar. So Z equals 2 over 5 over 1 over 5I. And it is in the algebraic form. Algebraic form. So simple. We replace Z prime by 1 plus I. Cross multiplication, Z bar to one side. Then we solve for Z bar. Part 2. Verify that if Z is real, Z prime is pure imaginary. If Z is real, we will Z is real either Z is real بتكون Z equal X يعني imaginary Z equal to 0 or argumentless Z equals 0 plus 2k pi or pi plus 2k pi. For a complex number to be real, either the imaginary part is 0 or the argument is 0 or pi. In this case, verify that if Z is real, Z prime is pure imaginary. Z is real, I can Z in the form equal X, where X is a real number, not imaginary number. X belongs to R. So I put instead, if Z equal X, it means that Z bar equal X, because the conjugate of real is X. So I replace Z bar by X here. So Z is real part 2. Z equal X and Z bar is also X. Now Z prime is 2iz bar over 1 minus Z bar. Z prime is 2iz bar over 1 minus Z bar. Z bar is X, it will be 2ix over 1 minus X. I can write it as 2x over 1 minus X times I. Here Z is different from 1, yani we have Z different from 1. Yani X different from 1. So this is 2x over 1 minus X is real. Times I is a pure imaginary. So Z prime is a pure imaginary number. So if Z is real, Z prime is pure imaginary. Z is real, I will repeat. Z equals X. Replace Z bar also X. Replacing Z bar equal X. In the given relation, we get Z prime is pure imaginary because the real part is 0. Real Z prime equal to 0. I can say real Z prime equal 0. It means that Z prime is pure imaginary. Part 3. Write Z prime in the exponential form in case Z equal EI pi over 2. write z prime in the exponential form. In case z equal ei pi over 2. So it is easier first to change z into algebraic form, changing z to algebraic form, then replacing z by its value in this equation. We calculate z prime in the algebraic form, then we change z prime to the exponential form. Z equal ei pi over 2. I can put z equals 1 into cosine pi over 2 plus I sine pi over 2 equals cosine pi over 2 is 0 plus I equals I. So z equal I, z bar equal minus I. Now we replace z bar by minus I in this relation to get, so part 3, z equal ei pi over 2 equal cosine pi over 2 plus I sine pi over 2. Cosine pi over 2 is 0. Sine pi over 2 is 1. We get I. So z equal I. Z bar equal minus I. Knowing that, conjugate, we change the sign before the imaginary part. Z prime equals 2I over 2I into minus I over 1 plus I. It is equal 2 over 1 plus I equal 1 minus I. So I have to change it to exponential form. So z prime equals the modulus radical 1 plus 1 is radical 2 e to the power minus I pi over 4 by using the calculator. If you forget how to use the calculator, you can ask me on Wednesday. So z prime equal radical 2 e to the minus I pi over 4. This is the exponential form. So I replace z bar by minus I, بيطلع 2 over 1 plus I. By using the calculator, we get 1 minus I. Also by using the calculator, we can calculate the modulus, which is radical 2, and the argument minus pi over 4. This is the exponential form. The exponential form, who is z equals, or z prime equal r e I theta. Now, part B, is z prime power 10? Is z prime power 10 real or pure imaginary? Justify. Now, z prime power 10, I have z prime in the algebraic form. But z prime to the power 10 is difficult to expand. So to know if it is real or pure imaginary, I determine the argument of z prime to the power n. Argument of z prime to the power n. We have the rule, argument of z power n equals n argumentless z. If this argument is 0 or pi, then z power n is real. If this argument is pi over 2 or minus pi over 2, so we can say z power n is pure imaginary. In our case here, Part B, argument of z prime to the power 10. He 10 argument of z prime plus 2k pi. We have determined this argument is pi minus pi over 4. 10 into minus pi over 4 plus 2k pi. This is the argument of z prime to the power 10. Equal minus 5 pi over 2 plus 2k pi. Minus 5 pi over 2 is more than one rotation. Minus 5 pi over 2, I can write it as minus 2 pi minus pi over 2. Minus 2 pi is one complete rotation. I can skip it. Minus pi over 2 plus 2k pi. So z prime power 10 is pure imaginary since the argument is minus pi over 2. I will repeat here. Argument of z prime power 10 is 10 argument of z prime plus 2k pi. A property, we put 10 here. 10 into minus pi over 4, it is determined in the previous part. So we get minus 5 pi over 2. I can write it like that, minus 4 pi over 2 minus pi over 2. Minus 4 pi over 2 is minus 2 pi. I can skip it, remains minus pi over 2. Part 4. Show that OM prime equals 2OM over MB, OM prime. You know that the distance is the modulus. So whenever you have a relation between the distances or the lengths, we have to use the modulus of the given relation. We have to use the modulus of the given relation. We have to use the modulus of the given relation. Remember that the modulus of z bar equal modulus lal minus z equal modulus lal z. Modulus of z1 times z2 equal modulus of z1 times modulus of z2. Modulus of z1 over modulus of z2 equal modulus of z1 over modulus of z2. So here in this exercise, we have part 4, z prime equals 2i z bar over 1 minus z bar. So modulus of z prime equal modulus of the numerator, which is 2i z bar, over modulus of 1 minus z bar. Now here it is a product. I can put it modulus of 2i times modulus of z bar. But here I cannot calculate the modulus if it is written like that. I put it is modulus over the overall. So it is modulus 1 minus z bar. Now, modulus of z prime, modulus of 2i is 2, radical 0 square plus 4 square equal radical 4, which is 2. Modulus of z bar is the same as modulus of z property. Modulus of z bar equal modulus of z. And modulus of 1 minus z, all of it bar, equal modulus of 1 minus z. Modulus of z prime is the distance. Z prime has an image m prime. So modulus of z prime is the distance from O to m prime, OM prime, to Zm, this one, I can write it like that, step by step. I can put modulus of Zm prime equal to modulus of Zm over 1 is Zb minus Zm. So OM prime will be equals to OM over Bn. OM prime, modulus of Z prime of M prime equal OM prime. Modulus of Zm is OM over Bn. Now part 4b. Deduce the set of points of M. We are going to find the set of M if M prime moves on a circle of center O and radius 2. Part B, determine. Part B is related to part A. M prime moves on a circle of center O and radius 2. M prime belongs to a circle of center O. Yani OM prime is radius. Yani OM prime equals 2. I put instead of OM prime is 2. So part B, M prime belongs to circle of center O and radius 2 means OM prime equals 2. 2 equals, this is OM prime is 2, equals 2 times OM over BM. 2 and 2 are simplified. So BM equal OM, BM equal OM. Since M is equidistant from O and B, M belongs to the perpendicular bisector of OB. M belongs to the perpendicular bisector of OB. Now 5 part A, show that Z prime plus 2I into 1 minus Z bar is pure imaginary. Here don't expand. The easiest way is we replace Z prime by its value. Z prime by its given value. 2I Z bar over 1 minus Z bar. So you have to replace Z prime by its value. So Z prime plus 2I into 1 minus Z bar. Z prime, I replace it by 2I Z bar over 1 minus Z bar. Plus 2I is plus 2I into 1 minus Z bar. So first step, I replace Z prime by its value. I take the common denominator here, which is 1 minus Z bar. 2I Z bar, 1 times 2I is 2I. 2I times Z bar is minus 2I Z bar into 1 minus Z bar. 1 minus Z bar, 1 minus Z bar. 2I Z bar minus 2I Z bar, which is equal to I, which is pure imaginary. It is simple. Just replacing Z prime by its value. LCM, simplify, we get 2I. So don't expand. Part B. Deduce. Part B, we are going to deduce that if M moves on a circle of center B and radius 1, M prime moves on a circle whose center and radius are to be determined. Deduce from the previous part. So whenever we need to determine the set of points, we use the modulus. We use the lengths. Lengths is determined by the modulus. So I use this relation that you get from 5 part A, and you put the modulus of each side. So this is the relation that I have got from part A, Z prime plus 2I into 1 minus Z bar equals 2I. Now I take the modulus of the product. I put modulus here. equal modulus of 2i. The modulus of the product equal modulus للفيرست modulus of z prime plus 2i times the modulus of the second 1 minus z bar equals modulus of 2i. Also, I cannot find the modulus like that. This modulus, I put it modulus of 1 minus z all of it bar. Now z prime plus 2i into 1 minus z all of it bar equals modulus of 2i is 2. Radical 0 square plus 4 square equals 2. So z prime plus 2i modulus للconjugate equal modulus without conjugate 1 minus z equals 2. Zm prime 2i is minus za. Always this one should be minus. We cannot put it plus. Zm prime minus za into zb minus zm equals 2. Zm prime minus za into zb minus zm equal 2. In am prime times bm equals 2. But it is given here m varies on a circle of center B and radius 1 means bm is 1. bm is 1. So instead of bm, I put 1. Then m belongs to a circle of center B and radius 1 means bm is 1. am prime equals 2. The distance from A to M prime is 2. The M prime varies on a circle of center A and radius 2. AM prime belongs to a circle of center A and radius 2. Part 6. Part 6 show that x prime equals, in this part we have z equal x plus iy, z prime is x prime plus iy prime. So you replace z by x plus iy, you replace z by x plus y, and z bar by x minus iy in the given relation, and we get the value of the real part of z prime and the imaginary part of z prime. You replace. So here we have z prime equal 2i into x minus iy. This is z bar into 1 minus x minus iy. We expand 2ix minus 2i squared. يعني بتصير plus 2y over 1 minus x plus iy. We multiply by the conjugate. The conjugate of the denominator is 1 minus x minus iy. I change the sign before the imaginary part over 1 minus x minus iy. We multiply by the conjugate of the denominator. Now, the denominator, we get a real part square, which is 1 minus x squared plus imaginary part squared, not iy squared, the imaginary part squared, y squared. 1 real part squared plus imaginary part squared. We expand. 2ix times 1 is 2ix. 2ix times minus x minus 2ix squared. 2ix times minus 2iy is plus 2xy. 2y times 1 is 2y minus 2xy minus 2iy squared minus 2y squared I. Missing here I. Now 2xy minus 2xy 0. Then x prime is the real part. The real part here only 2y over 1 minus x squared plus y squared. This is the real part. y prime is the imaginary part is minus 2 into x squared plus y squared minus x. This is the imaginary part. This, and that. I take minus 2 common, it remains x squared plus y squared minus x over 1 minus x squared plus y squared. This is y prime. So x prime, we get x prime and y prime. So here, don't expand, don't cross multiply. ما تعملوا cross multiplication. Only replace that by its value, multiply by the conjugate, then you will get x prime and y prime. Now 5 part B. Determine the set of points of M when Z prime is real. Z prime is real. Z prime is real. يعني the imaginary part of Z prime which is 0. Z prime is real يعني imaginary Z prime is 0 يعني Y prime equal to 0. Z prime is real يعني the imaginary Z prime equal to 0 means Y prime equal to 0. This is Y prime here. Minus 2 into x squared plus y squared minus x equal to 0. Cross multiplication. We get x squared plus y squared minus x equal to 0. This is the equation of a circle. To find the center, نتذكر شوي. السنتر هو A, B. A is minus coefficient للx over 2 minus coefficient للy over 2. So minus coefficient للx over 2 minus 1 over minus 2 is half. Minus coefficient of y is 0 over 2 is 0. So M belongs to a circle of center half 0. Radius is radical a squared plus b squared minus c. This is a. This is b. C here, no constant here. C is 0. So we get half. R equal radical a squared plus b squared minus c equal half. So Z prime is real, يعني imaginary Z prime 0, يعني Y prime 0. We get the equation of a circle. From this equation, you get the center and the radius. Part C. Let D be the straight line passing through B and parallel to the y-axis. Show that as M varies on D prime, M prime varies on a straight line to be determined. نحن ال B, ZB is 1. And B is 1, 0. This is the orthonormal system. This is B, 1, 0. And this is the line D. This line will have an equation x equal 1. Since it is parallel to the y-axis, its equation x equal 1. We are going to find that M prime varies on a line to be determined. So I take these x prime and y prime. I put instead of x 1 and I will check what we will get. We replace x by 1. So x equal 1, then x prime equal 2y over, this one can't, x minus 1 squared, 1 minus 1 squared plus y squared equals 2y over y squared equal 2 over y. Y prime is equal minus 2 x squared, it becomes 1 squared plus y squared minus 1 over 1 minus 1 squared plus y squared. This y prime here, we replace x by 1. We get minus 2y squared over y squared equal minus 2. So m prime belongs to a straight line. Here it is not constant. X prime is the variable. Y prime is minus 2 remains constant. So m prime belongs to the straight line of equation y equals minus 2, which is parallel to the x-axis. Part D. Show that if Bm equal radical 2, then x prime equal y. If Bm equal radical 2, I need to prove that x prime equals y. You know that Bm is the distance between B and M. Bm is the distance between Bm. How to calculate the distance between 2 points? It is the modulus of Zm minus Zb. Here, Bm equals radical 2. Bm is Zm minus Zb modulus. Bm is the distance from B to M. It is x plus Iy minus 1 equal radical 2. This is Zmx plus Iy minus Zb is 1 equal radical 2. The distance, or the modulus, is the real part square, which is x minus 1 square plus y square. The modulus is the real part, x minus 1 square plus y squared equals radical 2. So x minus 1 squared plus y squared equal to, by squaring the two sides, x minus 1 squared plus y squared equals 2. I need to prove that x prime equal y. I take x prime. X prime is equals 2y over 1 minus x squared plus y squared. But 1 minus x squared plus y squared is 2. This one is 2. So x prime equal 2y over 2. It is equals y. 2y over 2. We get y. Okay. This is all for this video. Next time we'll continue part 7. Please read the notes, write the notes, and if you have questions, you can ask on Wednesday. Yalla, see you.